X-ray are invisible light with enormous energy, powerful enough to see through matter. But when we look at the spectrum, two puzzles appear. First is the existence of lambda minimum for a given voltage, and the second one is the mysterious peaks. Classical physics cannot explain either of these. They are pure quantum fingerprints. In this video, we will uncover how lambda minimum and those mysterious peaks arise and why only quantum mechanics makes sense of X-ray spectra. To understand these special features, let us recall how X-rays are produced. Take an evacuated tube. When energetic electrons emitted from the cathode strikes a metal target, which is usually a high melting point material, X-rays are generated. Two key facts are observed here. Higher the energy of the electron, more the penetration of the X-rays. And when more electrons are bombarded on the metal target, the intensity of the X-ray increases. But to go beyond these basics, we need to see how classical physics explains the continuous part of the X-ray spectrum. From classical electromagnetism, we know that whenever a charged particle is accelerated or decelerated, it emits electromagnetic radiation. Now, in the setup which I have shown before, energetic electrons strike the metal target and are suddenly decelerated. This rapid slowing down of energetic electrons is the reason why X-rays are produced, and this is known as Bremsstrahlung radiation or braking radiation. The higher the energy of the incoming electrons, the more energetic the emitted radiation will be. And when the electron passes close to a nucleus with a large positive charge, it experiences a stronger deceleration. In other words, target with high atomic number produce more intense braking radiation. If we combine these two, then this will lead to more energetic radiation. So, classical physics does explain one part. That is, the continuous spectrum of X-ray arises from the range of possible electron deceleration inside the target, but it cannot explain the lambda minimum nor the appearance of the characteristic peaks. In quantum mechanics, we already know the photoelectric effect from my last video. Here, photons strikes a metal, transfers its energy and ejects electrons. Now imagine the reverse. Instead of a photon giving energy to electron, energetic electron transfer its energy to the metal atoms, and this energy is released as photons. This is essentially what happens in X-ray production. You can think of it as an inverse photoelectric effect. Electrons in, photons out. This quantum viewpoint is crucial because now the emission of photons is governed by the energy conservation at the quantum level, not just by continuous deceleration. And this is where the explanation of lambda minimum and the sharp characteristic peaks begins. For a given target material, say tungsten, and a given accelerating voltage, experiment shows that the X-ray spectrum always has a lambda minimum. Duane and Hunt measured this and proposed an empirical formula, that is the relation between lambda minimum and the voltage. Now let us explain it using quantum physics. The work function of metal is only a few electron volt, but in X-rays tubes, the electrons have energies of the order of 10 to the power 4 to 10 to the power 5. So we can safely assume that nearly all the electrons' kinetic energy is converted into the energy of a single photon. Under this condition, we can get this relation. Here, nu max is the maximum frequency of the photon, and corresponding to this, we can have a lambda minimum. Now, if we rearrange this, then we will get this expression. When we substitute the constants, this expression exactly matches with the empirical formula. This shows that quantum physics, through proper energy quantization, can explain the existence of lambda minimum, something which classical physics could never account for. Here we see the spectra of tungsten and molybdenum, both taken at 35 kilovolt. Notice something important here. The lambda minimum is the same because it depends only on the applied voltage as we discussed earlier. But in molybdenum spectrum, we see sharp characteristic peaks. Where did this come from? To answer that, we need to look at atomic transitions, a purely quantum concept. When an electron absorbs a photon whose energy exactly matches the gap between the two levels, it jumps to the higher level. This shows up as an absorption spectrum, that is, dark lines where intensity drops. On the other hand, if an electron is already in an excited state and falls back down, it emits a photon equal in energy to the level difference. This gives the emission spectrum, that is, bright lines on a dark background. On the left, we see a schematic diagram of atomic energy levels. Notice that the outer levels are closely spaced while the inner levels are separated by much larger energy gaps. When transitions occur between outer levels, the energy difference is only a few electron volts, and this corresponds to visible light of the optical spectrum. But when transitions occur between the inner levels, the energy difference is much greater, 100 or even thousands of electron volts. This energy falls in X-ray region. So only transition involving the inner cells can give rise to the characteristic peaks we observe in the spectra. When a high energy electron from the cathode strikes the target atom, it can transfer enough energy to knock out an inner cell electron, say from the K cell. This leaves behind a vacancy in the atom, an empty site that needs to be filled. Now there is a probability that an electron from a higher cell, for example from L cell, will fall down to occupy this vacancy. In doing so, it will release a photon whose energy equals the difference between the two energy levels. And since these are inner cell transition, the photon lies in the X-ray region of the spectrum. This kind of process will give rise to the characteristic peaks in the X-ray spectrum. Let us come back to the spectrum we saw earlier, that is shown on the left, and on the right we have the atomic energy levels of molybdenum. If we calculate the photon energy for transition from L cell to K cell and from M cell to K cell, the corresponding wavelength matches exactly with the two prominent peaks in the spectrum, and they are known as K alpha and K beta line. So, the characteristic peak, it is due to the transition happening in the inner energy levels. In the same way, other elements can show additional peaks like K gamma or L lines depending on the shell involved. In conclusion, the continuous spectrum is explained by classical physics, but the existence of lambda minimum and the sharp characteristic peaks are explained only through quantum mechanics.